Okay, thank you very much. I'm Mark Campbell from Cornell University. So I'm going to sort of give my slice through this problem. I think autonomy in aerospace systems is there's a lot of different aspects to it, and I think we'll touch on a bunch of those in the 4 different talks and probably in the panel. But I'll talk to you a little bit about my slice. Just a little bit about my background. During my PhD and early faculty time, I was all space systems, but I've moved more into robotic systems. So I have kind of that unique perspective that I'm going to try to bring today to that. So let me just talk briefly about autonomy and then lead into what I think the uniqueness is of aerospace systems. So autonomy is sort of very prevalent. People sort of might know a little bit about what this is. I don't think this is working. In the upper right is the Roomba. Does anybody have a Roomba in their house? Yeah, a bunch of engineers. I like that. So I think there's one over here.
Yeah, that'll work.
Does this work? No, not really. Thanks. So the Roomba is really great, and not only that, but we actually use them in our classrooms now, and they're really great for software and algorithm development, very, very fast. So if you're really looking at algorithm and theoretical work, they're a really great platform to kind of do it. This is an example of a small company called Kiva, which is working on warehouses and manufacturing, or warehouses and distribution. So I think Office Depot is one of their customers. So basically, you put in an order, and these robots would move around and take your order and get it to you as quickly as possible. Certainly, manufacturing I think has been around for a long time. Cars and those types of things, and now just in cars in general, there's a lot of autonomy, especially in the high-end cars. So I just saw a commercial 2 weeks ago about adaptive cruise control system that are now on some of the Mercedes, where you come up behind a car, you're in cruise control, and it senses the car and it automatically puts on the brakes for you. So, and I work in this area, and I'm not sure if I'd want that for my car. But let me, in aerospace systems, however, the autonomy it typically lags. I mean, when we had our sort of telecon to talk about some of this, we all agreed with this. And there's a bunch of reasons for that. This is sort of my take on that. The first, of course, is that human lives are at stake. I mean, you have, there's the shuttle and those types of things, some of those accidents that have happened. But of course, there's airplanes, right? So it takes a long time to develop these things, a long time to certify them to make sure they're safe. Of course, there's the environment. The environment of being up in an airplane is one thing. But one of the biggest challenges, and this was, I think, one of the huge challenges of trying to send people to Mars, was just the fact that you had to send them through the radiation belts outside of Earth. And that was really one of the biggest challenges. So the environment is very, very unique. Of course, public relations kinds of things. I think the early spacecraft had a lot of redundancy, and they tried to save some money by taking some of that redundancy out. But you have to ask whether that was necessarily the best thing, especially with some of these Mars missions that happen. Timescales. I'm not sure if anybody has seen some of the scenes of mission control of a mission that did not go well, but the people who were part of those missions have been working on those for 5, 10, 20 years. Maybe the scientists have been working on it for 20 years. And to see those things skip off Mars or something like that are really, really hard. So I put cost down here, all right? In parentheses, I think cost certainly amplifies these. It's not necessarily the main driver. I think some of these other things like safety and things like that are bigger drivers. So what I'm going to do is I'm going to focus on 2 things. Again, this is sort of my slice. I thought for a while what I would talk about, and I focus on 2 kinds of things. And one is what I would call the deeper intelligence in robotic systems. And this is leading a little bit into some of the things that Mitch was talking about, as taking the next step of having these things act a little bit more intelligently. So these are some of the examples that I'm going to talk about. The second thing is a tighter integration with humans with autonomy. And I think it's going to be kind of, I'm going to talk a little bit about some of these applications, not only just how this is sort of an operator controlling a UAV, but there's also sort of the interactions of personal robotics. Okay, so I'm going to, So this is a motivating example. So this is a car, so I'm not going to propose flying cars to you, but it's an example that we worked on that I think brings out some of the ideas of intelligence, okay, or lack of intelligence, I guess. So this is a project we worked on. Some people may have heard about it. It's called the DARPA Urban Challenge, and we were trying to, with a bunch of other teams, trying to design cars that could drive all by themselves in a semi-controlled environment with other cars. So no pedestrians or cyclists and things like that, closed course, so there's a bunch of safety measures. And we did pretty well. We were able to drive for about 6 hours and 60 miles and things like that, but there were a few hiccups, right? You sort of do your best for a couple years. You try to figure out what's going to, and then you throw it out there and see what happens. I think the complexity of this is pretty interesting, which is why I'm going to kind of show this. It really amplifies what I think are the challenges, I think, with intelligence, okay, which is taking an immense amount of data and then taking that into some type of information and then making some decisions on that, okay? And at least hardware-wise, I think we did a pretty good job of this. Back behind this, there was this was about 3 years ago, 24 dual-core machines networked together. We had all the data at our disposal. It was all time-stamped very, very precisely, which was really critical when we were actually driving around. So we sort of had our own mini cloud sitting in here, so it was actually pretty good. But certain things happened. So this is one of the things that happened. So this is a view of us sort of driving around. We're car A. I sort of took the other cars out. This is a view from a 64 scan laser that's spinning on the top of this. It's sort of that thing right here. So we're stuck here. We're trying to merge onto a right-hand turn, and we're stuck. We actually think the lane is blocked, but you can see it's actually not blocked, and we're just kind of going back and forth. So this car gets a little miffed at us, says, well, I'm blowing out of here. And about that same time, we do the same thing. We start taking off, okay? I always like this scene because if you look at this, if this was completely flat, these would all be circles, but when the collision actually occurred, they just sort of started rocking back and forth. So, this is an easy and a hard problem, right? We sort of do it all the time. On the other, so you think, okay, yeah, we could maybe automate that. But when you start stacking everything together, it becomes much more difficult. So in the end, like good academics, we wrote a paper on this together. In essence, we thought the road was too narrow. The actual place we wanted to drive over was very, very close to that cement barrier. And so we also didn't anticipate somebody coming around us because it was effectively a one-way road. We thought, the other car thought we were just stopped. Okay, and because we were kind of moving back and forth trying to clear out our sensors and thinking we made a mistake. So in essence, we didn't have this predictive capability that Bernie was talking about last night and things like that. We were just reacting to whatever was going on in the environment. So if you look at intelligence in robotic systems, I think currently, well, at least if you take a step back and think about it, robots work really, really well, and the tasks are repeated. There's not a lot of uncertainty and things like that. So this has been amplified a little bit. Certainly manufacturing, they've been in for a long time. Very, very repeatable tasks. However, for complex tasks, like I just showed, the intelligence just isn't quite there. Okay, so there's a bunch of things you can do this. Since I've been working on robotic vehicles, I guess over the past 3 or 4 years, we've started to draw a little bit more inspiration from humans because the humans do a lot of these things, more intelligently. So if you look at that as inspiration, making decisions under uncertainty is the big thing. Anticipation and prediction, learning, and doing strategic thinking. These are all things that are really, really hard in autonomy to do right now, and they're amplified anytime you have uncertain situations. So this is so I have sort of a couple of challenges underneath this big umbrella of intelligence. Okay, so this is a data replay of our car driving around campus. And so this is just one of our color cameras. It's a bit grainy because we only saved a lower resolution. This is this laser, okay, and it's basically plotting intensity level and things like that. But what's amazing about all this data is that you can see the sidewalks, you can see things on the side. We're going to come up here right about here. I think this was right around the holiday time, so people are leaving, so there's people crossing the street. Somebody's going to have a bag behind them and things like that. So you can see this is just really pretty amazing. This is all range data, okay, whereas this is all just camera data, okay? So I put this up here. I could, if I had security clearance, I could probably, well, I might not be able to show it, but I'm sure the, fighter airplanes and things like that have gobs and gobs of data like this. Some of the simulators that I've seen are just really, really pretty amazing. So the idea is that there's just tons of data, okay? And so I actually changed the title of the slide a little bit last night based on the talk last time. I think the first big challenge is that data is now easy. The hard part is converting that into usable information, okay? And now what is that usable information? For this, it would be object type and anticipation, things like that. These are all things that humans do pretty well, but are sort of trained and learned over time and things like that. So how do you take the data, because this is gobs of data, and we would have to develop some type of methodologies to bring all those things together. So after you do that, the next step then is how do you go from information to decisions, okay? So I'm going to give an example here, but again, humans are typically very good at this. But the idea, the big challenge here is that the information, all that information, not only is there a ton of it, but it's uncertain, okay? But in the end, you have to make a deterministic decision. So I always tell people that in the example of a car is you're driving down the road, you don't necessarily know exactly where everything is, but you come to the stop sign and you're not going to go right 70% of the way. Okay, you're either going to go right or you're not going to go right. So in the end, you have to make a decision based on all that uncertain information, and the humans are really, really good at that. And I think autonomy really pretty much lags behind so far. So it really requires a better information and also better connection between information and decision making. And there are some theories out there, but nothing that would allow things to work in real time or as uncertainties pop up. So I'm going to sort of show this movie. This is also something that happened during the challenge, which we didn't find out until about a week afterwards. But this is something we actually did well. I had to show something we actually did well in addition to the accident. But we're coming down a 4-lane highway, and there's 2 cars here. There's one other robotic vehicle, and then there's a following car. We're going to get into the other lane because we're going to try to make a pass. But what's interesting is we can't see the car in front of it. This is all just our gobs of data that are coming out from all the laser streams, and we have radar on the car and things like that. But what we do is we hang back here just long enough to make sure that they're actually in that lane. So effectively what we're doing is we're doing a nice job reasoning about the environment. And then when we start passing this car, we start tracking the car in front of it. So here's the second car coming up in front of it. And we, again, reason about it. Instead of going back into the lane, we effectively go past this car and then move back into the other lane. So we were pretty happy that we actually, in addition to doing some not so good things, we actually did some good things. And so let me switch gears a little bit and talk about UAV systems. So this is this is called the C-SCAN UAV. These are some collaborators from a company called In Situ, which is now a subsidiary of Boeing. This company originally came up with the founders originally came up with the Aerosonde that Jack was really talking about. So this is the interesting part about this one is its launch and its landing. So they wanted it to be able to launch off of boats and things like that. Because fishermen wanted to be able to use it. Of course, it has some defense applications and so on. But the launch is basically like a slingshot. So you'll be able to see this right here as soon as I play it. So it basically slingshots out, and so they can actually take it off directly from a boat. And then it lands, so this is it landing. And effectively what this is a long rope, and it has little clips on the end. So it actually flies into the rope, and it sort of gets caught by very much like a fly in a spider's web, and just lands exactly like that. Okay? So, but I put this example up because this is a UAV autonomous airplane example, or even if you think about the cooperative autonomous airplanes, because you have all the same challenges, information as well as decisions. The information in this case is locating survivors in a lot of clutter, okay, especially if there's been a hurricane or something like that. What is your detection accuracy with all of your sensors? So you might have gobs and gobs of sensors. Are you going to show all that to the human, or are you going to try to do some processing on your own? All right, if you do processing on your own, are you going to lower your detection accuracy? I mean, these are all pretty big challenges, I think, even when you start talking about the human-robotic interaction. Of course, occlusions, trees, and buildings, and things like that. You can make a number of decisions, either on board or let the humans work on those, like where to fly, if that improves your censoring and coverage, and what to share between the different elements. Okay, challenge number 3 is learning. So this is a map of that course that I was just talking about. And so this right here, what these black marks are every time we hit the brakes. Okay, so we want to plot these to kind of see what happened, where we were making mistakes and things like that. So this right here is actually when the accident occurred. The interesting part is that 18 times we came here and did exactly the same thing, which is that we came to that intersection and we slammed on the brakes and we sat there for about a minute and a half going back and forth trying to clear out our sensors, and eventually we sort of passed through there. So this is basically a setup of what was happening. And so effectively what was happening is where we wanted to go right here, even though it's a very, very wide lane, is there was just a small little concrete barrier that was sticking out that looked about the size of the car, and our map told us that this was only about 9 feet wide, and we didn't think we could fit through. So until we said, well, the heck with the road, we sat there and tried to figure out what was going on. Okay, and so there was a bunch of uncertainty we just really couldn't figure out. So the idea is that the humans could, we as drivers, we would come back to that and we say, okay, there's no car there, we'll just kind of continue through. But how do you do that with an autonomous system? Because what happens if you come back the next day and there really is a car parked there, right? You can't just say there's nothing actually parked there. So the question is, how do you do this safely and robustly? I think that's really what the big challenge is, and especially in aerospace systems. And I think some of our speakers will talk about that in a little while. This is an example of some colleagues. Peter Abil at Berkeley he's a faculty member at Berkeley, but did his PhD with Andrew Ng at Stanford. So this is some pretty funky things that they're doing where they had a stunt pilot come in and fly this autonomous helicopter, and then they use these reinforcement learning algorithms, apprenticeship learning, where they learn both a model and a data. Or a model and the controller in order to kind of do some funky things. So this is doing some barrel rolls, and they have some really interesting kinds of things they're doing. This is it sort of flipped over. It's pretty amazing what they can actually do with this. But the big challenge, because I think anybody who works on airplanes, I think Jack can probably back me up on this. If we would try to sit here and model that system and then develop controllers and try to do something like this, we just wouldn't be able to do it. It's just really too much of a challenge. So, but even with something like this, what happens if you move to a new environment? What happens if it's very much like the learning algorithms that the previous talks have been talking about. What happens if you take it out of the data set that it was learned on? So that's a bit more challenging. Verification, validation. So Stefan's going to talk a little bit about this, but the idea is how do you, I think this is sort of the big thing that I sort of saw yesterday in one of the talks, I think, was how do you evaluate robustness? Is it just testing, right? So certainly if you look at things like the Boeing aircraft that goes through years of testing before you can actually certify it and things like that. So it's a really challenging problem. In the robotic systems here, we basically had these steps, and I've sort of already talked about that. It took us typically about 2 minutes to kind of clear out the road and do things like that. So, but there's different terminology that's actually used in the community. Verification, validation, V&V is sometimes what it's called. But the idea is, how do you verify at the very, how do you incorporate this at the very beginning? Because maybe testing isn't the best way to do it, right? Because you're doing that at the very, very end. Why can't you incorporate some of that things at the beginning? So there's a lot of research out there now in model checking, especially on the computer science side, and connections between mechanical and computer science. Okay, so I'm going to switch gears a little bit and talk a little bit, my last sort of third of the talk about interacting with humans. So I have sort of two examples here as motivation rather than just sort of movie. So this is this C-SCAN UAV, and this is one of the operators. And you see there's sort of 3 screens in front of these operators. And I'm always struck by groups that build these just wonderful autonomous systems and then have no really great way of interacting with a human. So when these things first came out, there was 3 monitors, and 2 of the monitors looked like the data coming from the Matrix movie. It was just all numbers, and then this was just a video feed, and then the human would have to sit there and monitor all that for typically about 8 hours, and that's how they train people, and that's how they work. Okay, so this was sort of the inexpensive version of sort of what Jack was talking about in terms of the Predator, but I'm just always struck that nobody really. Or not nobody, that is sort of secondary in terms of what this interface should be. This is a small example. Personal robotics are really sort of becoming a hit these days, especially in terms of the home and things like that. This is a small little robot called Neo that one of my colleagues got, and I put this up here because there's an interesting story of this. It has a bunch of built-in functions, but you can do algorithm development on it. So that's sort of the key element of it. So they had this delivered about 2 weeks ago, and she handed this off to one of our undergrads and said, okay, meeting next week, get it to do something cool so you can show it. And it had all these built-in behaviors, so that made sense. So the student got all this stuff working. It was really, really great. And we had our lab meeting, about 35 people, put it up, and whispered into its ear and says, walk. And I'm not sure if you can see it. It has blue eyes. Those blue eyes turned red, And then it said, no. And, I expect that from my kids, but not really from the robots I'm trying to program. So, but there's, all these future movies and things like that have, these personal robotics, and I think certainly space is definitely going to have something like that. So I'm running a little bit at a time, but what my personal research is focused a lot on is looking at information types of missions and having a single human and a single UAV or robot, and then also groups of those. And so you can cast that as a feedback loop in some of those challenges. Some of those challenges are things like taking human information and robotic information and putting them together in some coherent form, and as well as interaction kind of approaches. So let me sort of talk about these last little bits, and I'll then finish up. So the first one is the fusion of these kinds of information. So I sort of pose this as a challenge. I've talked to Mitch about this a little bit and some of his colleagues at JPL. But the idea is that if you look at sort of rover operations and things like that, there's a lot of decision making that's done on the ground, and there's some autonomy up at the with the rovers, but there's this long time delay and things like that. So wouldn't it be nice to do something like take advantage of what the scientist knows, which is really looking at some of the data and saying, yeah, that's interesting, that's interesting, that's interesting, and I have this much confidence in that. And then the rover is taking all this data in situ at Mars about where everything is, about where rocks are, how I can drive, and things like that, and put that together in just one model, okay? But it's very, very different data. Could you do something like that? So we tried to do something like that, and we put it in the context of a search and rescue kind of thing. So this is just with humans. So these are a couple of my students. So what we tried to do is this is actually Cornell's campus. So this is about a half kilometer by a half kilometer. And there's a map in here. So this is actually the football stadium. My building is right over in here. There's a bunch of buildings over in here and so on. And then overlaid on that is a probability density defining where things may be. Okay, so you want to think of it as your prior information, okay, which you might have if you have some type of search and rescue inside of a building or those types of things. So what we want to do is take all the information that's coming, which is all uncertain information. Okay, so you have GPS, you have which way they're looking, which is why they have these helmets on. You have whether they detect or not correctly, because they're not perfect. Okay, and then what happens? Okay, and so we had 5 of these looking for 5 kinds of elements, and so this is just sort of a track of sort of what's going on. So they're going to all the peaks. We just sort of let them go wherever they actually wanted to go. They sort of went to all these peaks, drove around. Sometimes they could communicate, and sometimes they couldn't. So this is talking a little bit about the groups or fleets kind of structure and those types of things. Okay, so these are driving all around. But what's interesting is they would go inside of a building and lose GPS coverage. So what happens there is they might find something, but they might not know exactly where they're at. Okay, so all that information was being fused exactly like any type of human information. Okay, running a little bit out of time, so let me finish up here. We've also started to look at human-robot interaction and fusion, where the human and the robot are putting each of those pieces of information together, very much like the Mars example that I gave. In terms of interaction, so there's which way should the humans and the robots interact, the humans and the autonomy interact. So this is actually one example. You can certainly use voice, you could draw. This is sort of what the example is down here. It's somebody sort of drawing the interactive element here of, I'm selecting this robot, I want you to go over here. This is another example by some colleagues at University of Illinois where they're actually using brainwaves. So they actually sit there. So I guess this relates a little bit to the facial twitches, but what's interesting is that they're trying to control how a UAV flies just from their brainwaves. So they can't really blink very much because the signal is too large. So they actually have to be really, really trained in order to do something like this. So there's a bunch of different ways of interacting, and I haven't really touched on too much of those, but except for some of these things. But there's some really interesting elements of it. This doesn't look like a video game, and I figured maybe I got a comment on that. And the challenge here is that you're taking, you're actually trying to do something with that command and having the robot provably, look around the room or do something like that. Okay, so it's a pretty big challenge, I think, associated with that. Task coordination. how does what should the human do and what should the autonomy do? Okay, and I think this is one of the biggest challenges, because in the end, you want the human to do what they're good at, which is strategic thinking, all those things that I talked about. You want the robot to do what they're good at. So there's a lot of good approaches here. Sort of the classic feedback way is this adaptation, some type of online optimization, and there's a lot of work on that. These days, there's ideas of sort of embedding inside of robots and actually humans sort of models of what the other ones may be. So this is sort of like a good sports team or something like that, having some intuition about what the other person is actually going to be doing. And then the final challenge is scalability. This is another picture of air traffic control. So one of our Ella's going to talk a little bit about air traffic control and sort of scalability kinds of things. But once you go there, then you're adding a network on top of that. How do you do networking but also have it be certifiable and those types of things? It's a really challenging approach. Okay, so in conclusion, so I just want to sort of leave you with three things, sort of my three messages. The first is that I think aerospace provides pretty unique constraints in terms of autonomy. Certainly the fact that human lives are very much at stake, and the environment that these things would be going in, the costs associated with those things, and so on. So I personally believe these are the sort of the things that I'm most interested in, but I think they're very, very important to the future of these things, which is robust autonomy will require these kinds of things. One is, how do you go from data to information to decision making in a robust way? Now, remember, this feeds back through the environment, so any decisions you make will impact, what's going to actually happen next in terms of your data. All right, so it's not easy to kind of analyze, okay? Just analyzing this flow from here to here is easy, but when it actually starts feeding back, it's much, much more difficult. And how do you do it in a robust way, and how do you do it in a verifiable way? And the second one is how do you enable autonomy to be really an extension of the human? I mean, I think you want to think of it more as, okay, it's a tool that I'm actually using. And how do you get it to be able to do that? And that match, I mean, we've had times where if that match isn't good, they perform worse than if they actually were working on it individually. So having them work together is really, really important, and it's a challenge. So thinking of these more as one entity, I think, is an important thing to do. Okay, thank you.